All right. Hello, everyone. At least I hope there are some people out there. Welcome to my talk. I am Arthur Dwyer, and this is a talk titled, When Should You Give Two Things the Same Name? There we go. Hopefully you can all see that. Screen. All right, good. By the way, I also do C++ training, so if you like what you see here, you like my Zoom style, know that it is available to you for a low, low price. All right. So when should give two things the same name? This was a sort of philosophical talk that I wanted to give. This is not necessarily going to be of super great interest to the Boost crowd. But I think I'm going to say some somewhat interesting things. And I hope that you'll think so too. Or if you think that I'm saying wrong things, I hope you will speak up in the Q&A or in the chat and let me know. I've got question breaks scattered throughout the next 90 minutes. And I'm hoping also that this won't take 90 minutes. We'll see. As you see, we've got, 4 question breaks during the talk when I'll be checking the chat, checking the Q&A. Yeah, if you could interrupt me on the webinar, which you can't, but if you could, I would totally want you to do so. However, I won't be checking the chat during the talk, or other than the Q&A, other than the question breaks. If you say something in chat and I just steamroll right over you, it's probably because I'm not looking at the chat. All right. So this whole talk came out of a blog post that I wrote a while back, in which I made an analogy between classical inheritance and overloading of functions. And so the first part of this talk, I'm actually going to talk not about giving things the same name, but about deriving things from the same base class. I'm going to spend a few slides on that, and then we're going to go into giving things the same name proper. Copious anecdotes from the STL, kind of a major rabbit hole on constructors, because I found that interesting while I was writing the slides. And then I will somewhat undermine my thesis by giving you some ways it might be metaphorically true, in addition to physically true. And maybe some bonus mantras and takeaways. So suppose that I am a maintainer of some code base out there in industry, and I open up the code base first day on the job, and I see a class hierarchy that looks like this. I have a struct animal, and I have a struct cat that inherits from animal. And cat probably has some members, and there's probably some other stuff in animal as well we're not really concerned with, but the basic shape of it is that we've got public inheritance, and we've got some virtual methods. I see a virtual destructor. I see a virtual method there. What should we expect that the rest of this code probably looks like? Well, we expect to see that there's going to be some polymorphic function in the object-oriented sense that takes something like animal star, right? Or maybe animal ref, const animal ref, unique putter to animal, shared putter to animal, all of these things. Basically, it's going to take some kind of handle to an animal. And we're also going to see some place where someone creates a cat, otherwise that cat class wouldn't exist, and they're going to implicitly convert that cat star to an animal star so that they can pass it off to that polymorphic function foo. And we're going to see inside that foo, we're going to see some place that a cat is treated according to its animal interface. Specifically, we're going to see that that polymorphic function foo probably calls the polymorphic method feed through dynamic dispatch on that animal star parameter, right? Somewhere there it's going to say animal arrow feed. And or somewhere in there it's going to say, polymorphically delete this animal, right? We're heap allocating these things. We can tell because we're giving them virtual destructors, and also because that tends to go hand in hand with object orientation, right? And we can sort of have all of this intuitively in our brains just from looking at this one header file with animal and cat in it. We don't really need to see the rest of the code to understand that it probably has roughly that shape. So if we go and we look at the rest of the code, and instead we see that they're, returning cats by value, They are storing them on the stack. They're using functions like swap and the copy constructor. And then we're puzzled, right? This is not the shape of code that we expected to see based on that one header file with the classical inheritance in it. So it is very strange to use classical inheritance and virtual member functions and so on if what we intended to do with those classes was to write value semantic non-polymorphic code, right? That shape that we had led the reader to expect. Now, it's true that sometimes we do use polymorphic inheritance in C++ without using it for classical polymorphism. The empty base optimization, where we inherit from something just as a way of sort of getting it as a member, but it's a little bit more efficient to do it this way. By the way, C++ 20 introduces an attribute so that you no longer have to do this if you don't want to. So that's nice. The CRTP, the curiously recurring template pattern. We might have cat inherits from some base class that does not provide an interface, but rather provides an implementation, right? The goal of this inheritance here is that this base class can provide me an implementation of the fight with method. I'm not actually conforming to an interface there. I'm using my base class to provide an implementation, allowing me to conform to someone else's interface. There's no such thing as the can fight with interface. And of course, tag dispatch. The iterator categories use public inheritance, but don't use polymorphism. So C++, of course, has these corner cases, but I would like to treat them as corner cases, special cases that prove a general rule. And these are just inheritance, right? None of these use virtual methods. If you had virtual methods in your code and you did not use them for their intended purpose of polymorphic callers, that would be even more surprising. Why are you using virtual if you don't intend to have polymorphic functions? So the extreme form of this intuition is related to Liskov's substitution principle, which I went back and dug up the paper at one point, and this is a quote from it. If for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then we say that S is a subtype of T. So that this is expressed in mathematical terms, not in C++ terms. When we say S is a subtype of T, that's like saying, you could make S inherit from T, right? In a language that supports this kind of subtyping, this object orientation, which C++ does. And if we add intent to the picture, then we would say you should make class S a child class of class T if you intend to pass an object O1 of type S as the argument to some function P defined in terms of T, right? This is your polymorphic function P. If you don't have such a function in your program, if you have no foo that takes animal star, then there's really no reason for cat to inherit from animal, right? And if you have no such foo, if you don't intend to pass an object of type S as the argument to some function P, well, then I have a quote from someone else for you, William of Ockham, right? If you don't intend to use this thing for its purpose, then there's really no reason for that public inheritance relationship to exist. And therefore, lacking a reason to exist, it really should not exist, right? William of Ockham says entities should not be multiplied without reason. And I might add, programming techniques should not be introduced into your program without reason, right? Now, you might say, what's the technique here? Is it the use of polymorphism as opposed to the use of non-polymorphism? I would say yes. But there will come a time in this talk where you will probably wonder, who is it who decides that one technique is more complicated than the other and that one way is simpler than another? And the answer is me. I decide that. So yeah, keep that in mind. Right, so Occam's razor says make class S a child of class T if and only if you intend to have some function P defined in terms of T and pass an S to it. All right, so we've got intent in the picture. We've got simplicity in the picture. Who else can we quote here? one of my favorite quotations, and it's a little curmudgeonly, but also from one of my favorite mystery authors, G.K. Chesterton. Once in his railing against modern liberal reformers, they're awful. He said, modern reformer walks up to a fence in a field and says, "I don't see the use of this fence. This fence annoys me. Let us clear it away." And they just want to do that. But the more intelligent reformer, the more conservative one, looks at that fence and says, "I'm not going to let you just remove it because you don't like it. When you can tell me that you do see why this fence is here, then maybe I'll allow you to destroy it." In other words, he's saying fences are usually there for a reason, right? So just because you personally don't see the reason the fence is there doesn't necessarily mean that there's no reason for it to be there. And so you should try to understand why it's there before you go tear it down. And the same thing applies to a technique that you see used in a computer program. If my computer program uses classical inheritance and I say, classical inheritance, bad, I don't like it, I am going to replace it all with std variant or something, as the modern reformer might. G.K. Chesterton would very curmudgeonly say, first you need to figure out why it was using polymorphism in the first place. And then once you understand what it's doing with that polymorphism, then maybe you can see how to replace it. But just going in willy-nilly, removing things, removing techniques, is going to break whatever it was that actually used that technique, that relied on that technique. Fences generally have reasons, so tearing down fences should not be done lightly. And again, as programmers, we ask, I want to do this refactoring. Is this refactoring safe? The conservative answer is no. This refactoring is never safe, right? Whatever you're changing, something probably depends on it. There's reasons. So let's make it difficult to tear down these fences. If we take that as a given, then we have someone else. Robert Frost wrote a poem about fences and technical debt, how hard it is to maintain these fences once you've got them up. And near the end of that poem, he points out that this is a little bit of a pain, maintaining this fence. And before I built a wall, I'd ask to know what I was walling in or walling out, right? Fences are tech debt. Tearing them down is hard because G.K. Chesterton is going to stop you. He's going to say, no, you need to understand that fence before you tear it down. So before you put it up, you should make sure that you have that reason, that you know that reason, and that you document that reason for the maintainer, right? Erecting a new fence should be done only for a good reason, so that when it comes time to take it down, someone else will be able to figure out the reason it was put up in the first place. If you go putting up fences without reasons, well, then you get in a sort of paradoxical situation, right? Before we can tear down this useless fence, we have to understand why it was put up. And if it had no why in the first place, it's going to be harder for us to understand. So a fence that has been put up for literally no reason at all is going to be massively harder to remove than one that was put up for a good reason. And the same is true of code, right? Techniques used in code. Someone using a technique in code just because they, read about it, they thought it was cool or something, or they just weren't thinking, and they didn't even realize that they were using a technique. Entry point. Every single method is virtual. Why? As far as I know, it's just because they thought, well, the virtual keyword's kind of cool. Let me just put it here. Right? But because you can never be really sure, were they thinking they were going to write a mock for it one day, or maybe they did and it got deleted, or right? It's hard to go in there and say, well, I'm just going to get rid of those keywords. So my experience of industry code bases is that this happens a lot. People using techniques for reasons that are not obvious, and it turns out down the road, well, they didn't really have a reason at all. But per Chesterton, if you can't even understand why they were doing it, that actually makes it harder, not easier, to get rid of. So that makes G.K. Chesterton very annoyed in that picture there. So getting back to C++, as a reader and maintainer, when we see this class hierarchy with the virtual methods and the inheritance, we expect it to have some reason by G.K. Chesterton, by the Chesterton's fence. And we expect it to have one specific reason in particular in the context of C++. We expect the Liskov substitution principle to apply, and cat inherits from animal specifically because we have a polymorphic function P that takes a handle to an animal, takes a handle to a cat and treats it like an animal, right? If we don't have that, then we get very confused, right? If you aren't being forced into one specific inheritance hierarchy by the Liskov substitution principle, that is, if you don't have that P, if you don't start with that P and then work out S and T from there, if you go the other way around and you say, well, I have S and T, what relationship should they have to each other? You can imagine all sorts of different possible hierarchies. Say I have a square and a rectangle, right? The silly example from a lot of textbooks, but some textbooks will tell you that a rectangle is a square, right? Because a square has one sort of dimension and a rectangle has that and another dimension. So a rectangle is a square, or maybe a square is a rectangle because a square is a rectangle plus some constraints. That actually works out a lot better because in math, we would say that every square is a rectangle. But you could imagine doing it either way, right? If you have no reason in your code to do it one way or the other, right? You could say that both rectangle and square, they are siblings. They both inherit from quadrilateral or parallelogram. Right? You can make up any entity you want, but you shouldn't. That's William of Ockham. That's Occam's razor. Right? Don't introduce entities you don't have a reason to introduce. And in fact, the common wisdom is don't introduce an inheritance hierarchy without a reason. Prefer composition over inheritance. So if you just are observing the fact that a rectangle and a square have a lot of things in common, well, pull out those things into something like a shape component and indicate that a rectangle has those things and a square has those things, right? There's no is-a relationships happening here, no classical inheritance at all, because we are not being forced into it by the Liskov substitution principle. And if we are not forced to put up a fence, then we should not put up that fence. I'm going to switch back and look and see if there's anything in the chat so far, or feel free to ask questions, etc. Oh, there's all sorts of stuff. Excellent. Yeah, cat content. All right. Yes. Arthur decides what is right. And people observing that I'm talking about fences. Yes. There will be nothing about memory fences in this talk. But I did think of that over and over as I was writing these slides. Roland says, many times one hits the why is this done in such a way? And there's absolutely no code comments or anything about the why, but lots of comments on the how. Yes. I'm not entirely sure I understand what you mean by the how, but yes. Yeah. It's a common anti-pattern to see, ++ I semicolon / increment I, right? The useless comment. It says how it's done, which you can see from reading the code. That's the entire point of the code, is to explain to the computer how it's done. You don't really need comments on the how, but comments on the why, that's the great thing, right? It would be nice if every fence came with a sign hanging on it that said, this fence is here because there's a bull on the other side. Or this fence is here because I got bored, right? If only they had those signs, then it would make it a lot easier to figure out which of those fences were necessary. Yeah. And if it ain't broke, don't fix it. Indeed. All right. Let us continue onward then. So this talk was really talking about when to give two things the same name. So my personal bias was encoded in the name of this talk, right? This was not called when to give two things different names. The implicit assumption that I made in the title of the talk that you all chose to come to, so I can assume you all share my implicit biases, is that things have different names by default, that we have a single name for a single entity. So in general, we should use different words to refer to different ideas. And when referring to the same idea, it would be nice if we all used the same word. Now, in society in general, that's not always practical, but within a single industry code base, that would be nice. I ask myself all the time when I'm looking at code or standards proposals or anything, what is the name of this thing? If we can just figure out what the name of it is, then maybe it will be a little bit clearer what it does. And I suspect that I stole that and probably the phrasing of that from Tony Van Aert, who I think I've heard say similar things in the past, right? Figure out what its name is, then maybe you'll know a little bit more about what it does. So naming is important. When referring to the same idea, we should use the same word, and referring to different ideas, we should use different words. And specifically when programming in a language like C++, any given single identifier should refer unambiguously to a single entity, right? Now I've switched to using C++ terms, right? Identifier and entity. And what do I mean by that? Well, which of these code bases would we prefer to deal with? Here I have code base A that has two functions, two different entities, both named feed. They both use the identifier feed. They just take different parameter lists, right? But they are in an overload set together. And then in code base B, I have two different identifiers, feed underscore snake and feed underscore bear. Those are completely different identifiers. There is very little possibility they will be confused. Now notice that they both use the English word feed, right? Feed is a part of feed snake and feed is a part of feed bear. Hopefully this refers to the same general idea, right? It would be unfortunate if they meant different things. For example, maybe feed bear means you give food to the bear, but feed snake means you give the snake to something that eats snakes, right? That would be confusing. A C++ identifier to refer to two different entities, right? Whereas in B, we have two different identifiers for the two different entities. So B, I claim, makes William of Ockham happy. A makes William of Ockham sad. And I'm sure if he were alive today, he would be like, whoa, what is that? With the four wheels going very fast. But if he were alive today, he would probably look at this and say, this is not at all what I meant by multiplying entities. But it's similar, right? I would say, yeah, it's similar. Here we have two entities with the same name. Here we have only one entity per name. Yeah. So using a distinct identifier for each distinct entity in your program makes things a lot easier, makes a lot of things a little easier. Number one, if you are a Luddite like me using bad IDEs or no IDEs at all, using a lot of git grep, using a lot of sed, it makes it easy to jump from a function call to the definition of that function because there's only one possible destination, right? You just say, where is this function defined? And well, there's only one function by that name. You don't end up with a screen full of, well, did you mean this feed or that feed? I don't know. You're supposed to tell me. You can do a grep for all uses of the entity, grep feed. You can detect when an entity only has the definition and no uses. That means it's unused and it's obsolete, and you can probably just get rid of it. In fact, you can definitely get rid of it, right? I don't think there is any situation in C++ where an identifier can be in your program and have no uses, and you couldn't just get rid of it. The exception being names that are magic to the standard library, such as begin and end and swap and return value, all the coroutine stuff, and get now because of structured bindings. They're just making it super complicated, but at least there's still a single list of those names you can find somewhere that these names are magic. And of course, global renaming also becomes very easy if all the uses of this identifier in the program refer to that entity you want to rename. When two entities have the same identifier, all of these things become harder, right? I can't say I'm going to rename the feed of snake method to feed snake, right? Going the other way is easy. But here, I have no way of knowing just from the output of a simple text processor like grep, whether this feeds a snake or a bear, right? It's not obvious from the call site. I have to go actually trace through the code. Hopefully, I can use something like libclang to tell me whether this feeds a snake or a bear. But maybe not even that, right? A few things also get easier for the computer. Overload resolution gets easier if all your overload sets have size 1, so that might speed up your compile time. Teeny bit, not really, Don't use that as your justification. And jump to definition in your IDE also gets easier. Sometimes IDEs make mistakes, but if it is literally impossible to make a mistake because there is only one entity with that name, well, then you don't make mistakes. Therefore, I say overloading should have a reason. I say overloading is more complicated than not overloading. And by Occam's razor and Chesterton's fence and Frost's corollary, Robert Frost's corollary that says if a fence is going to be hard to get rid of, then when you put it up, you should know why. Right? So when we see this code that has two different functions named feed, taking different arguments, I look at this code just like I looked at that Liskov substitution principle code. I look at this code and I say normally two entities should have two names. To have some reason because of Chesterton's fence and because of Frost's corollary, right? That when you do something, it should always have a reason so that other people can figure it out, so that they can undo it when it turns out that you did it wrong. So we expect the overloading to have some reason. And in fact, I claim we should expect it to have one specific reason. What's that reason? Overloading enables polymorphism, right? Just like the example we started with, where classical inheritance enabled runtime polymorphism, overloading enables static polymorphism through templates. Here I have a function template called solve puzzle. It takes a reference to an animal, where here animal is a template parameter, right? So this is like T, right? I'm just calling it animal to make the parallelism come out a little bit better. So I take some kind of animal. I don't even know what it is. There's no constraints on this template at all. And I call feed on it. So here, any kind of animal that I can call feed on, I can pass it to solve puzzle. Right? When I give two entities the same name, such as the feed of snake and the feed of bear, I am effectively saying that I'm going to use this identifier within some kind of template. That's what you're telling your reader when you do that, right? Because giving things the same name, overloading them, enables static polymorphism. If you're not using static polymorphism, you shouldn't really be using overloading. You shouldn't really be overloading things like feed here. Here's a real example. Just show what I know what I'm talking about, maybe. We've got vector and list, both in the STL. I've simplified them here. They don't need to be templates for this example. Now, many different STL containers, including vector and list, reuse the identifier pushback. So vector has a pushback, dec has a pushback, list has a pushback. Forward list, I think, does not, right? But many of the containers have pushback, and it's named the same in each case. And so looking at that, I say, what is being enabled by all of these different things, all called pushback? And the answer is, in the STL, CppNow provided, or someone provided, back inserter. So back insert iterator is a template whose implementation in its assignment operator, as it happens, calls pushback on some kind of container. They don't know what it is, right? My container here is something of type T. Oh, I didn't actually show it, but container is a T star in this example. So any T that has a pushback can be used with the back insert iterator template. So I'm able to write this bit of statically polymorphic code that works with all of these different classes. If instead I had pushback into vector and pushback into list and so on, I would not have been able to do the static polymorphism that I'm doing here. I wouldn't be able to write back insert. Another example is swap, right? Many types overload their own swap, and it's found by our and this is exactly isomorphic to our example with feed, right? That I have a function that swaps to snakes and a function that swaps to bears and so on and so forth. And when I call swap of x and y, just looking at that one line, I cannot tell whether this line is swapping to snakes or to bears, right? Unless I know what x and y are, I don't know what this line of code is doing, and I don't know which entity it's actually using. Maybe one of these swaps is actually completely unused, and I could remove it from my code. But I can't tell just by grepping for the word swap because it shows up like here. I don't know which of these two swaps this is called. So all else being equal, right? Occam's razor, I would prefer to see swap snakes x and y, which then lets me know immediately it's calling the swap of snakes, right? And it's not just that it's telling you that X and Y are snakes. I almost said that out loud, and I do want to make that distinction, right? It's not that this line of code is self-explanatory. This could be like swap 47, right? It doesn't matter what the identifier is, as long as it is unique. And I can find, go and see exactly what the definition of that entity is. So all else being equal, I would prefer these two swap methods to have different names, swap snakes and swap bears. But all else is not equal, right? In the STL, swap is overloaded so that we can use static polymorphism, so that we can write a templated std sort or a std rotate, right? All these things depend on all of these different types T, all having their own thing named swap. Now here's a counterexample, also from the STL. Every STL container provides two overloads of erase. It has two methods, both named erase. So I'm giving two things the same name. And of those two things, one of them takes two const iterator arguments, and the other takes one const iterator argument. And really all this one is doing is just erasing, the element pointed to by where. So from where to where plus one. That's all it's doing. It doesn't really need to exist, but it's in there. So there's one identifier, erase, controlling two entities. What static polymorphism is enabled by this? What template do we have that might sometimes call erase with one argument and sometimes call erase with two arguments, so that we need them to have the same name? Well, I claim none, right? Having these two different kinds of erase doesn't really enable any clever template. This is a fence without a reason, and it's a super awkward fence, right? For decades, modern reformers have been walking up to this fence and saying, ouch, that hurt, right? Because we have a vector here of 10 integers, and I'm using the erase remove idiom to say remove all the odd ones and then erase them from the vector, right? Shuffle all shuffle the even ones down so that there's garbage at the end. And then I use v.erase and I chop off that garbage. And now I can assert that none of the things in my vector are odd. And I run this code and the assertion fails, right? And it fails because I forgot the second argument to v.erase, right? This is the two argument erase that I should be calling when I use the erase remove idiom. But it's very easy to forget that comma v.end, right? It's very easy to run into this fence in the dark when you're not looking for it. And it doesn't have a reason to be there. It's not like there's a sign on it that says, this fence is here because there's a bull on the other side. There's not. There's nothing on the other side. This fence is totally pointless. And so Robert Frost says, we should not have put this fence up. Right. Question break. I was beginning to think it would never come, actually. Nothing new in the chat. I'm also going to do a quick time check here. All right, we're like half an hour in. All right. I'm going to proceed then. Oh, there's something in Q&A. I should look at that. All right. Yes, there's two questions, at least in the Q&A. Anonymous says, slide 21. Yes, I don't think I made a big deal about it, but notice that I had slide numbers. I always draw people's attention to them because I see people still in the year of our Lord 2021 making slide decks that don't have slide numbers. I'm trying to stamp that out. All right, so the question is this an argument against auto? I don't think so. It's an argument against giving multiple variables the same name. And you might say, well, I have tons of variables named I. But it's definitely an argument against having a bunch of global variables named I in different namespaces, right? I would not do that, right? There's a sort of a principle that someone probably came up with at some point that basically relates the length of an identifier to its scope in the program. The shorter names like I and J, those are going to be scoped to a very tight loop. Then you have like one-word names that are in like a function scope or class members. And then for your global variables and so on, you're going to use like really long, possibly mangled names. Maybe prefix them with G or something to really make them unique. So it's really easy to tell when someone's using one of these very widely scoped names. But as far as their types, I don't think that I'm saying anything about their types here. I don't think that I'm saying anything about long right. Slide 23. Does this mean that if I had my own container, say my special vector, and I was not planning to use it with back inserter, should I give it pushback into my vector instead of just pushback? Excellent. Not really a question, right? Because you know the answer. You probably should name it pushback. So is that a hole in my argument? Perhaps. And we will see a little bit more about that later. No, I would, if I had my special vector, of course, I would not name its pushback function differently unless it really did something different. Matthias says, what about the contactor scope when using things like swap? Do you consider the possibility of being misused higher? You mean the fact that swap is a global function in the global namespace and it's has a very short name? Honestly, if I were designing a standard library for a C++-like language from scratch, I probably would not use all these short names like begin and end and size and swap, and data that we just keep adding to the standard library's customization points. I probably would give them longer names, namespace names, figure out a different way other than ADL of doing customization in the first place. But in the context of C++, in the STL, I think we're stuck with it. So Adam said, what about namespaces? Do these interfaces have the same or not the same names? Here I have an engine audio : iManager and an engine input : iManager. And this is something I've seen in a lot of industry code bases. And this is the sort of thing that I say, please don't do that, right? Please do have, engine : audio manager and engine : input manager, right? I would say that those two iManagers have the same name. They're both class iManager. They are in different namespaces. That's how they're able to be two different entities. But it is the fact that they use that same identifier that makes them have the same name. That they're literally two different entities in two different namespaces, and they have the same name, same identifier. So yes, we're going to talk a little bit more about namespaces in the second half of this talk. Whoops. And then Chris said in the chat, for pushback as a specific example, if there was no back inserter, would you recommend using a different name per class? Short answer, yes. Controversial for sure, but yes, I think if there were no back inserter, then you would name things differently unless you had in your imagination the idea that there would be a back inserter at some point in the future, right? The back inserter, which is to come after me, you think that back inserter is going to exist at some point, so you're going to design your code to support that use case, even though you're not literally using it yet. And we will talk a little bit more about that as well. All right, so I am going to proceed. We're going to go down a rabbit hole, and then we're going to come back to those questions about namespaces and pushback and try to get a bit more clarity about that. But while I was writing these slides, I went down a rabbit hole. So here's an unfortunate example, constructors. When I think about overloading in the standard library, what has the biggest overload sets of all? Constructors, right? Every STL class has like 30 different constructors, and they're all doing different things. Many STL types just have too many constructor overloads. I picked string as an example. Now, of course, string is an example of having too much of like everything, right? Too many methods, too many ABI incompatible versions, but certainly too many constructors as well. So here I wrote just a smattering of the 30-something constructors that string has. And I picked specifically the ones that take two arguments of primitive type. So we have a constructor that says, give me n copies of this char. We have one that says, give me the first n chars of the C string pointed to by this const char star. The third one says, give me a copy of this other string starting at this position. So that's a fun one, right? These two the two middle constructors here can both take a quoted string literal. If you put an S on the end of it, you get the second one. If you don't put the S on the end of it, you get the first one. And they do completely opposite things, right? And then there's a templated one here that takes any two input iterators as well. And so this is a fence in the Chesterton's fence sense. This is a purpose. This fence must have a purpose, or else something is wrong. And this is a very annoying fence. We would like to tear this fence down if we could, right? Because it leads to things like this, where I have a std string of 0, 0. In case A, 0 here is a size t, and the other 0 is a integer literal, which can convert to char. So this is going to call the first overload, and it's going to give me 0 instances of the character 0, null byte. With B, let's see here, 0 with a z is size t, which means this literal 0 here is a null pointer constant, and this is calling the second overload, and I think having undefined behavior. So this fence leads to all sorts of just weirdnesses. We would love to get rid of this. We would love to replace most of our constructors with factories. Now we're going to see why we can't do this for string, but in an industry code base where you control the code, particularly where you have a lot of business logic types that maybe do have different ways that they are created, all else being equal, prefer to replace all those constructors with static factory methods. So here I'm giving string a bunch of static factory functions. String : from copies of, string : from putter and length, string : from suffix starting at, and so on, right? And each of these is a static method that returns a constructed PR value string, which is totally efficient these days, by the way. Since C++ 17, we're not paying a penalty for like making copies of the return value or anything, right? That this is perfectly efficient, hence removed. But constructors are special, right? All else is not equal. C++ has a love affair with constructors. So this is the reason for the fence. Factory functions are great. They are self-documenting. I love them and use them on business logic classes, but they do not work with the many perfect forwarding wrappers in C++ in the standard library. So in the standard library, we have things like std make shared, make unique, emplace back, emplace, variant in place. And all of those are all statically polymorphic function templates, right? Make shared is a function template, emplace back is a member function template. And they are statically polymorphic over a specific name, which is t, right? The name of the constructor. The name of the class itself is the name of its constructor. And so all of these things are using something like placement new and hitting that constructor. If you want that behavior, if you want to be able to use make shared, you need a constructor. If you want to be able to use vector and place back, you need a constructor, right? Because it's going to forward along those arguments to your constructor. It's not going to forward them on to some random factory function it doesn't know the name of. It's going to hit the constructor. And so in A1 here, this is totally okay. I'm forwarding along these two arguments to std strings constructor. In A2, I could write this, but this is super ugly, right? I'm saying use my factory function to give me a temporary string on the stack, and then move construct that onto the heap. So this is ugly. This is also an extra move. So here I am paying a performance penalty for my decision to use factories instead of constructors. Constructor syntax is the most convenient way to create an object that is somewhere other than the stack, right? If I want a temporary t, I say, given some arguments, make me a t, and then I can put that in a variable on the stack. Or I can say, given some arguments, make me a t on the heap, The new keyword means make it on the heap. Otherwise, this looks exactly the same as the previous line. Given some arguments, make me a t. Make it where? On the heap. And by the way, there is a new auto as of C++17. Guaranteed copy elision or deferred temporary materialization means that it is just as efficient. So I can, using a factory function, I can say t : from some args, given some args, make me a t, and then I can describe here in this identifier, I can describe how it is that I'm going to use those arguments. I have a place to do a little bit more description in my code, and that's always good. Or I can take that factory function, call it, say, make me a t, make it where? On the heap, using new auto. Or I could repeat the word t here. Of course, that means the same thing, right? Saying whatever the type returned from t : from some args is, make me something of that type on the heap. This, by the way, does not do a second move. As long as from some args returns a PR value, we have here sort of a recipe for creating a t. And where are we going to create it? We're going to create it with new. So there is no move construct happening there. That's great. So if this syntax is all that I had, the t : from some args, and I didn't have constructors, and I wanted to write a generic make shared template, how would I do it? Well, you wouldn't, right? The reason that we push everything into constructors in C++ is so that we can write make shared and then place back and so on, right? Overloading enables polymorphism. If we want to have that, I heard that I dropped out around slide 33. All right. Well, let's give this another shot. All right. Don't worry, this is the least essential part of the talk anyway. So if we want a statically polymorphic make shared template or build shared template that can perform the create operation on an unknown type t, we have to make sure the create operation has the same name for all the types t that might be used with that template. So instead of saying, let's overload the constructor with a whole bunch of different signatures as our generic way of creating objects, I could invent a generic way of creating objects. I could say the static factory function create generically is the way that we're going to do that. So I have this build shared function that calls t : create generically. And if you want to use your type with build shared, you're going to provide some member of your class named create generically that can accept arbitrary arguments and do something sensible with them. This is not particularly better, right? The constructor has a very generic name. That was our original problem, right? Several slides ago. Our problem was that these two calls to create std strings did vastly different things, but it was not apparent from their names, right? They have the same name, but they do very different things. And create generically has the same problem by design, right? Many different overloads of create generically, they all have the same generic name. So this fantasy build shared function that we have that we're replacing make shared with, it could instead take a kind of creation as a parameter. It could take a how parameter, and we pass in the name of the factory that we want to use. We pass in as a function pointer in this case, right? From copies of, we pass in a function pointer to from pointer in length, and so on. In today's C++, though, these have to be function pointers because they need to be concrete types, right? The compiler needs to be able to deduce what is the type of the how parameter here. So it has to have a single concrete type. It can't be an overload set, so that we can deduce that argument's type. Can we do better? Yes, it has been repeatedly proposed, and I like this idea. Not really sure why it keeps getting shot down. Core language syntax for lifting an overload set into a lambda object, so that you could say lambda introducer string from copies of. And then no matter how many overloads or defaulted arguments or how many templates had the same name, this would expand out into basically a lambda that took a bunch of arguments and passed them by perfect forwarding to string from copies of, right? or whatever the name here is. Sadly, this proposal never went anywhere. However, there is another proposal, P1170, also from a couple years ago, but I'm not really sure what happened to it, but maybe it's more active. It's certainly a more modern take, and it involves more magic. This is Barry Revson's P1170, introduces a new magic type called std overload set, which is just like initializer list. This is a library type that is created by core language syntax. So when you have a function that takes a std overload set and you pass it something that is just an identifier that is not a, this is not something that can be passed to an ordinary template. If I just took a parameter named how, this would not work. But here I'm taking a parameter of type overload set of how. And so compiler magic kicks in. And what I get here is something essentially like that lambda we saw on the previous slide. So how would be something of, the decal type of this lambda. And when I call it here, I'm basically just calling that lambda. And so this allows the call E, not the caller, but the call E, to opt in to say, this particular parameter of mine might be something like an overload set. I want to enable passing overload sets. In the same way that you might say, this parameter of mine might be a braced initializer. I'm going to enable passing braced initializer lists to me using std initializer list. So again, I think this proposal has been seen a little bit. I'm not sure where it's gone. It's certainly not C++ 20. I don't think it's on track for 23, but it's an exploration of this idea. What idea? I don't know. We've got way off track. Let's get back on track. Meanwhile, also, can people still hear me? All right. Seeing no questions. I'm going to proceed. So to recap so far, all the way back, forget that little digression. Sometimes we give two entities in different classes the same name with the same signature because we're going to template on that class type T, or in this case, animal, right? Multiple kinds of animals all have a .feed method. That .feed method's name is important. We're going to give them all that same name to enable us to write the solve puzzle template. And sometimes we give two entities in the same or different classes the same name with different signatures because we're going to template on the argument types, right? Solve infocom puzzle here, you have to provide not just the animal, but you also have to say what to feed it. Give me a list of foods and then, this example being exactly isomorphic to the standard make shared, right? Just here, this function, the polymorphism is happening on the name feed, and in make shared, the polymorphism is happening on the name the constructor. So all STL containers provide an insert method, container.insert, add a position, that's an iterator, comma, and then a value to insert at that position. But we have these associative containers that are kept sorted, like std set, std multiset, std unordered map, and so the pause in that case is just ignored, right? They just ignore the pause. There are some complexity guarantees, I think, but basically they just ignore the pause. Overloading here enables static polymorphism. What is enabled by every single container having the insert with the same signature? Insert iterator, right? The fact that we can say std inserter, and I can have an inserter into a vector, an unsorted vector, and I can say I'm going to copy this data onto the beginning of the vector. Or I can say here, I'm going to insert all of this data into the set, which is kept sorted. And so it's not really like I'm inserting at the beginning of the set. I'm inserting in whatever sorted order. But both of these lines compile. And more importantly, they both use this single statically polymorphic function template, std inserter. Right? Std inserter is one piece of code written just once, one piece of source code, behaves differently depending on the arguments I pass it. That's polymorphism. Just a couple of days ago on Slack, I heard someone say that set.insert of x should really be named set.insert or get of X because it doesn't always do the insertion, right? The set doesn't always get one more element. Maybe that was a collision, and then it doesn't insert. To which I might say, well, number one, maybe you have the wrong mental model of what it means to insert something. Maybe to insert into a set doesn't always mean you make the set bigger. That's not how we're using the word in this particular technical context. That's a little bit of a cop-out, though. I think the fundamental position is reasonable. There's no reason that set.insert of X needs to be named insert. Right? We could pick any name in the universe that we wanted for that function because it doesn't need to have the same name as any other function. As far as I can tell, there was never anything in the STL that required set.insert of X to have the same name as set.insert of pos comma X. Right? There's nothing that is statically polymorphic over that particular overload set. We don't use erase and insert, we use extract and insert, but we use insert in both cases. And I don't think there's a physical reason that we needed to use insert. We could have used adopt, for example. Same identifier for set and multiset. They both have an insert, but this could have been insert into set, and this could have been insert into multiset. And I don't think anything would break in the entire library. So William of Ockham would say, maybe we should have given them different names. It would make it easier to keep track of things. Same identifier for the range version as well. Yeah. But they all do the same thing, basically. So, shouldn't they have the same name? And in code bases where you get to choose, I say firmly, no, they should not have the same name. Right? This is that distinction we had at the beginning between using the same word for the same idea, which is excellent. These are basically the same idea. We should use basically the same words to describe what's happening in each case here, except maybe the node animal one, which again is a little weird. But just because you're using the same English word doesn't mean you need the same C++ identifier for these entities. It would be a lot clearer if we could have, for example, insert at for the 2-argument version versus just plain old insert. And then if what you've got is a node handle, we'll say insert node handle. And then if what you've got is a pair of iterators, first and last, we can say insert range, right? And then that distinguishes, if I see somewhere in my code set.insert of X comma Y, and I'm not real sure what X and Y are, then it makes it clearer if I see insert at X comma Y or insert range X comma Y, right? That can also help me understand the code. So by reusing right? We are making a wall, you're making a fence, and we should like to know what we are walling in or walling out, right? We're making a trade-off, trading off clarity for doesn't seem like anything. Well, what about switching containers? One of the great benefits of the STL, I mean, I give a course on the STL dimension, I do training, and one of the things that I bring up is that the STL is designed for uniformity of interface. Here I have a piece of code that used to use std_dec, and someone looked at dec and said, well, dec is random access, but it's not contiguous. So I would actually prefer for cache locality to switch it to use vector. And I can switch my container from dec to vector. And all of this code, these 5 lines down here, these are all pieces of code that worked just fine with dec. And as soon as I replace dec with vector, they continue to work just fine. We can easily switch our code from vector to dec, or even list. This code would work fine as a list, or multiset. This works fine as multiset. And we might do this again for iterator stability guarantees, that we're not moving things around. We might do it for performance, contiguity, cache locality, complexity, right? Swap out a map for an unordered map. So it's useful that map and unordered map have the same names, have the same API, because it makes swapping them around easier. Wah, wah. Did you notice that these containers have the APIs that look exactly the same, syntactically identical, but they have vastly different semantic properties? Did you notice that by changing from std_dec to std_vector, this code's behavior became undefined? Why? Because pushing back onto a dec does not invalidate iterators. Pushing back onto a vector does invalidate iterators. And then when I say erase down here, now I have undefined behavior if the vector reallocated. Right? So it's not really an unvarnished win, right? What is it the Hulk says? Whatever he says, this is not this. It's not an unmitigated win in this case. But it's something. In fact, we can think of extending this thesis from the realm of the code base, specifically the physical realm, to the mental realm, right? I'm writing one piece of source code that I then instantiate for many different types, but maybe I'm not writing a piece of source code I instantiate. Maybe I have an idea in my head about how I do STL programming, right? How I push back onto a container. And I have that in my head, and I'm instantiating that mental template for these different types, one at a time, over the course of many years. Titus Winters says software engineering is programming integrated over time. It's not just about what's in the code today. It's not just about the programming. It's about integrating that over the next 10 years and making decisions that will last. So the above code demonstrates absolutely no reason for vector erase and deck erase to share the same name, right? This overloading, the fact that the two erases have the same name, does not enable any static polymorphism. We have no C++ templates in our program that call t.erase first and last on an arbitrary t, right? This never happens. I never have some template that's instantiated for both vector and deck. But integrated over time, here I have a timeline. Our program at time t equals 1, our program at time t equals 2, and at one time, I used erase on a vector, and at a later time, I switched it to use erase on a deck. And I have some human that is instantiating over those two timescales and looking at the code yesterday and then coming back to the code a month later, and some details have changed, but erase still works the same, right? So when we look at this in a larger picture, maybe we're not looking just at the physical templates. Maybe templates can be mental. Maybe this destroys my whole thesis. Maybe it doesn't. Maybe you think my thesis makes more sense. Sharing names can also be used as an upgrade path, speaking of software engineering. The STL introduced string view in C++ 17, and it reuses a lot of names that std_string had. In fact, as we add things to string, we also add them to string view and vice versa. So here I have a function trimmed name. This is a C++ 20 function using our brand new, awesome, ends with accessors. We're getting contains, I think, as well. So if the file name ends with PNG or JPEG, then chop off the end of it and return it. We have a lot of overloading going on here. We have subster, string.subster and stringview.subster are two different entities with the same name, subster. Similarly, ends with, right? Now, do we ever in our programming, does anyone in industry anywhere in the world write a template that calls subster and then is instantiated for sometimes for string, sometimes for string view? No, absolutely not. It's not enabling static polymorphism, but it's enabling upgrading this code, refactoring it from the current use of string to the use of string view without having to rewrite all of the identifiers in the code, right? The Chesterton's fence reason behind giving these two entities the same identifier in this case is to allow us to do the upgrade, right? We just replace const std_string_ref with string view. And in this specific case, because we're returning a trimmed version of the string view, we don't even need to make a copy of it. I can just return a string view as well, and this will all work totally fine. This is a little bit cheaty because stubster on a string view returns a string view. If it had returned a string, I would be returning a dangling string view here, and this would actually be wrong code. So again, right, remember that Debbie Downer slide, watch out. But this is the kind of thing that we're enabling by using the same name for different things, right? But Chesterton reminds you, there should always be a reason, right? We found the reason. That's good. But if we can't find a reason, that's bad. This was arguably the same reason that std optional has the star and arrow operators, right? There's nothing about optional that's really like a a pointer or that implies that you should be able to get at the thing it contains by using star. We don't do that for like a vector. You don't say, give me the first thing in this vector with a star. Oh, you do it with brackets. I don't know. All right. But this enables upgrade paths, right? A C++ 11 or 14 program might use a unique putter to represent, maybe I have a certificate, maybe I don't, right? Maybe this connection is secure, maybe it's not. So if it is insecure, I will have this unique putter be null. Otherwise, I will have this unique putter point to a certificate. And then we get the ability to use optional and not do that heap allocation. So I say, all right, I will replace my unique putter with optional. I will replace make unique with make optional. And in connect here is my temporally polymorphic code, right? I am not using static polymorphism. I'm not using templates, but I'm using that mental template. Over time, this code's meaning changes from it used to be instantiated with unique putter. Now it's instantiated with optional, and it works for both, right? They both have conversion to Boolean. They both have an arrow operator. Works fine. Of course, really the reason that std optional got these operators is that it got them from boost optional. But where did boost optional get them? Well, it got them from unique putter or something like that. But reusing names can still lead to bugs. And in another context, completely different context from the last slide, I have found optional suffer a little bit from its reuse of some names. This is something that also applies to the smart pointers. Here I have a business logic data cache that has a couple of methods here. It's got like update, it's got a reset that maybe clears out the cache. And then a connection maybe has a data cache, maybe it doesn't. And in this function here, I'm saying, well, if I have a data cache, then I would like to reset it, right? Clear out that cache so that I can put more stuff into it. But what did I do here? Here I said, if I have a data cache, and I forgot to use the arrow. I used the dot instead. So I'm not saying reset the cache. I'm saying reset the optional. Did you know optional has a reset method? Just like unique putter and shared putter and so on. It means set it to null. So I used to have a cache with stuff in it. And I meant to have a cache with nothing in it. But instead, what I ended up with was no cache at all. Now I haven't got a cache. Okay. So instead of calling data cache : reset, I accidentally called tilde data cache. I destroyed the data cache. Here, of course, the blame really lies with data cache itself. It has probably no business using the verb reset here. It should probably have used, at best, the verb clear, because this is more analogous to what vector is doing. And maybe even better, something like clear data cache, right? Give it a unique identifier. Makes it easier to grep for, makes it a lot harder to hit this kind of typo. If I had called it reset data cache, there would not be a bug here. It just wouldn't have compiled. Okay, so the members of std optional are mostly named the same as unique putter because upgrade paths. Really, we inherited this from boost optional. And the reason that we kept the same names between boost optional and std optional is, again, upgrade paths. So you can do a little bit of macro metaprogramming here. I can say, if we are in C++ 17 or higher, then I will include the standard optional header and use std optional. Otherwise, I will include boost optional HPP, and I'll just use boost optional instead. All right, this is very common. You see this kind of thing these days for file system, for format, and for ranges, right? To say, if we have standard ranges, I'll use that. Otherwise, I'll use range v3 or nano range or something like that. The APIs in those two libraries are largely identical, and the reason for that is so you can have the same code base with just a macro to switch between, using standard ranges and using range v3, for example. It's not template-based static polymorphism, but it is, in a sense, on how I compile it. This technique is also known as polyfilling. If you haven't heard that term before, that's a great takeaway from this talk, the term polyfill. Here, boost optional is a polyfill for the standard optional. If you don't have the standard optional, you can fall back on using boost optional and it will work. And another reason you might see macro-based static polymorphism is platform-specific code. Here I have two namespaces, and I have identifiers in these two namespaces, I'm reusing the same identifier for two different entities. One is curses clear screen, the other is con.io clear screen. And then down in my actual main program, I pass in which terminal library would I like to use, curses or con.io, and just use everything out of that namespace, and it all works. But it's important that these functions, clear screen and clear screen, draw at and draw at, have the same name. If I change their names to like draw with curses and draw with con.io, then that would break my main program, right? That would break this technique that I'm using. I have introduced the technique of sharing the same name, two identifiers or two entities with the same identifier. That's a technique, and I'm using it to enable this polymorphism down here. Okay. Oh, good. Question break. 4243, would Liskov say that the differing iterator and validation semantics should dictate different names for deck vector pushback? Liskov proper does not apply. There's something here about concepts, right? Concepts are very similar to classical inheritance, where we have the concept at the top and it has lots of different models. That's very similar to having an interface at the top and lots of different implementations. Concepts in the standard library do carry with them these sort of semantic constraints, right? A regular invocable looks exactly the same as a normal invocable. Ordinary invocable. They look the same. They have the exact same syntactic requirements. But the one says, well, if you're claiming to be a regular invocable, you'd better also, be idempotent, and not necessarily the case for the other one. So we could imagine making some sort of concept for like, STL container, random access container, and then, putting some sort of semantic invariant on it, saying, if you claim to conform to STL container, then these are the operations that are allowed to invalidate your iterators. And then vector is like a slightly weaker form of that with more things that can validate. But in general, putting that hierarchy there is A, hard, and B, the whole point is don't introduce the hierarchy if you have no use for it, which I don't at the moment. So I think Occam would say, don't involve Liskov, unless you have a reason. And then hopefully your reason pushes you in the direction of figuring out. Anyway, yes, right. However, having the same name for pushback in both cases here, remember that did enable static polymorphism we are enabling. It is a benefit and not a drawback at all. The pushback has the same name in both cases. Question about Rust type traits are more explicit in opting into polymorphism. Would I support such mechanisms in C++? I don't support anything, but you mentioned concept maps. What are they called? But yeah, the idea of being able to specify my thing is a random access iterator or is a mutable buffer or something. But I did just name it a little bit weird. But here is the mapping that tells you how to make a random access iterator out of my thing. That would be super useful. And my understanding is that is what concept maps were in C++ OX concepts. And that would be awesome. And we missed the boat on that. And I don't think we're getting that. But if I were doing the language from scratch, yes, that's absolutely awesome. However, does that have much to do with opting into concepts? Not really. I mean, in specific case of iterators, we opt in anyway by saying iterator category, et cetera. And I have another talk from several years ago at, I think C++ Now, called The Best Type Traits C++ Doesn't Have, where I talk about how to opt into semantic constraints like that, particularly triviality of various things, right? Sure, we support the operation syntactically, but we are additionally warranting that it's trivial. And for that, you have to have an opt-in mechanism. And tag invoke, I have not really been following, but my impression is that that is that create generically factory from earlier, and it doesn't really solve any of the problems it sets out to solve, as far as my biases are concerned. But I have not really been following it. All right, let us proceed onward. So speaking of optional, in one of my talks just half a year ago at CppCon, I gave a back to basics talk on optional and variant and so on. And I gave this example of what not to do, something that is sort of seductive with optional. People might think about trying to do it, and I wanted to head them off at the pass and say, don't do this. Here I've got an API called Open Connection, and you give it a host name and you give it an optional certificate. If you give it a certificate, it will open a secure connection. If you don't give it a certificate, it will not open a secure connection, right? And so we use a default argument for that so that you can call this with 2 arguments or just 1 argument, or even explicitly passing it null opt to indicate, yeah, on purpose, I want an insecure connection. So this API looks great. It covers all the bases. There's 3 different ways you can invoke it. How many more ways could you want? It's perfect. But I think attributed to Michelangelo, was it, who said, you know, no, he said you cut away everything that doesn't look like Moses. But who was it that said it's not done when there's nothing more to add, it's when there's nothing more to take away, right? Think about that. But here we've got 3 different ways to call Open Connection. So we feel very proud of ourselves, but I want to say, no, that is complicated. That is a technique. You are doing overloading here by providing these 3 different ways of calling Open Connection. Even though there's no physical overloading going on, you're providing different signatures for the same name. And so I really don't like this. In a real code base, I would expect that you're going to use Open Connection in exactly one of 2 different ways. The first situation, the common pattern I say, is that this is some sort of internal implementation kind of API. Every caller passes in an optional cert that they got from somewhere else, right? The config file, they got it from someone who got it from someone who got it from someone. And nobody ever actually calls it with just a single argument. The default is completely redundant, right? What you really see as the way people call this is they pass in the host name and they pass in this optional certificate they got from somewhere else. And they don't even know whether it's valid or not, right? But they're never putting an if and saying, oh, if it's invalid, then I won't pass that argument. No, they're just going to pass it in. So the totally unused default value anti-pattern. I see this all the time in Python as well, but to a lesser extent in C++. But if this is the pattern, then we actually, A, should not give it a default, and B, shouldn't make a copy of it, right? In the old version here, I was saying I take an optional cert by value. But if I know all of my callers already have an optional they're passing in, I don't need my own copy. Just give me a reference to theirs. And this will be just as efficient, in fact, more efficient if these are stacked many levels deep. The second common pattern that I see is that this is a user-facing business logic API. All of its callers are business logic. Every caller knows whether they want to open a secure connection or insecure connection. And just like with erase, which can be called with 1 argument or 2 arguments, the ability to quietly forget that second argument is a massive liability. It causes bugs. It does not in any way help anyone, right? This is exactly isomorphic to our example with erase, where we had erase at and erase range, and we gave them the same name, and it caused bugs. If we just kept them as different names, we wouldn't have a problem. So this is 2 different jobs, should be 2 different entities with 2 different names. Here I have open insecure connection and open secure connection. One of them is a 1 argument function, the other is a 2 argument function. And here I don't take there's no optional in the picture at all. I just take that certificate. And so here, if I meant to open a secure connection, but I left off the cert by accident, I get a compiler error. So that's great. That solved a bug that we had, or a pitfall, a source of bugs that we had in the nice, attractive API. And notice that these 2 common patterns complement each other. I could have my business logic that all it does is wrap up the cert in an optional and pass it to the backend, which is that the one that doesn't take a default argument and just always takes an optional cert. Of course, in that case, I don't need optional at all, and it's actually a pessimization to introduce optional here, because then I would have to make a copy of the cert to put it inside the optional, and the whole point is they've already got the cert. So instead, I'll just use a raw pointer. And if the pointer is null, then there's no cert. So a function with defaulted arguments behaves a lot like an overload set. It behaves a lot like multiple entities that all have the same name, but different signatures. And so it is a technique. Like Frost's fence, it must be justified. You must have a reason to use default arguments before you start putting them in, just like with overloading. And by the way, I have a blog post you should read. If you've heard me talk at all, you know that I think default function arguments are the devil. And in the design and evolution of C++, I cherry-picked a quote that says, default arguments are logically redundant and at best a minor notational convenience, and that the reason that they were there, right, the Chesterton's fence reason we got default arguments at all was that we didn't have overloading, right? C++ didn't have overloading. Well, C with classes didn't have overloading for years and years, or months and months. And they tried to make do with default arguments and finally said, you know what, we need overloading. And then that was the better tool, and default arguments just stuck around for backward compatibility. But they cause problems. Default function arguments are the devil. That's me, you can quote me. Speaking of people from this century, another relevant mantra here, which you may already have been thinking of in the back of your head, is Eric Niebler once tweeted a couple of years ago that although concepts are constraints on types, you don't find them by looking at the types in your system. You find them by studying your algorithms. And this is essentially what we've been doing throughout this talk. When deciding whether to give two entities the same name, we look at how they're going to be used. We look at that static polymorphism or runtime polymorphism. Study the algorithm, study that polymorphic function, that caller. If the algorithm, if the caller doesn't need them to have the same name, don't give them the same name. If you don't have an algorithm that requires a certain concept, don't make that concept and then have everything, you know, shoehorned into to try to fit into that concept, because you don't need it, right? William of Ockham down there in the corner. Bonus content here on enumerators. I see I'm somehow running out of time, but when we give class members or free functions the same name, we can exploit that through templates. Enumerators similarly can have the same names but be in different namespaces. I've never seen this in real life, but theoretically, going down the little rabbit hole here, if I had two different enum classes, two different scope enums, which both had an OK, you know, anywhere in them. Here they're both with value 0, but it could be anywhere. And then I could say, you know, no matter what kind of error I get back from getContents, I can take its decal type. Oh, sorry, this E should be an error, right, I guess. And if it is its own decal type's OK enumerator, everything went fine, and otherwise it's not, right? Like you could statically polymorphic function template on two enums. I've never actually seen this done. I don't think it should be done. But if I saw multiple enums with the same identifier in them, I would start thinking, I wonder if they're going to do this. And if they're not, I think this is stupid. I don't think they should be doing this. Don't give two things the same name if you're not going to use that. Chesterton's fence. So our takeaways. Final slide here. So number 1, inheritance is for sharing an interface. If you're not sharing an interface, if you're not going to treat a cat as an animal at some point, don't use inheritance. That's the Liskov substitution principle. And I add, and I have a blog post on the subject, so is overloading. Overloading is for sharing an interface. If you're not going to share the interface, probably don't do overloading. William of Ockham said use a single name for a single entity. Well, he didn't really say that, but close enough. G.K. Chesterton said when you see two things that have the same name, assume there's a reason for it. Right? Fences have reasons, so don't go tearing them down, or go look for the reason before you tear it down. To which Robert Frost says, when you have the option to give two things the same name, don't, unless you have a reason. Right? Don't make work for the maintainer down the road figuring out what your reason was. Eric Niebler said, to find concepts, don't study what your callees provide in common, study what your callers require. Did I mix that up? I guess it depends which way you think of as the callee. Yesterday, I was thinking callee caller because it's a function calling other things, but if you're passing the things in, I guess it's the other way around. Yeah. And finally, yours truly says default function arguments are the devil. So, all right. With that, I think we are finally at the end of the talk. And are there questions? Let's see. What's your take on the many overloads of STL algorithms like transform reduce that all have execution policy projections? Yes, that was my timer saying you're done. Yes, I know. What's your take on all of these algorithms that have like execution policy being optional and then comparators being optional, et cetera? Should they have different names? The ones that take comparators, yes. I would like to see a sort and a sort with, right? Sort with comparator. Now, of course, with all of these things, as soon as you start picking different names for things, you run into the fact that there are only so many good names in the world, right? So I'm like, sort with comparator, sort as, like, I don't know what the name would be, but it certainly doesn't need to share a name with std sort, right? Same with execution policy. I cannot think of any reason off the top of my head to have a std sort and a std sort with an execution policy in the same overload set. I would rather see sort and parallel sort. You would have a whole parallel STL, right? They even called it that. And yet somehow they didn't put parallel in the name of the algorithm. Projections, I think similarly, right? A lot of these, I think the standard library is doing to avoid grabbing a lot of names, right? The standard library itself, part of its reason for having the fence there is names are expensive and hard to get rid of names once you've introduced them, right? So the standard library almost has the reverse policy of don't use too many names because you'll never be able to remove them or change the meaning of them down the road. So everything is named sort. And then later, if we find out that we did sort wrong, well, we still use sort with or sort as. Those names are still available. So yeah, we saw that with random shuffle, I guess, right? That was an example where they say, oh, we did it wrong. We're going to take out random shuffle and put in regular just shuffle. They actually got win a shorter name because they said, this time we got it right. We'll see. But with thread, went the other way, right? With thread, they were like, oh, well, let's call it JThread, I guess. Yeah. Yes. If there are more questions, I can certainly take them. Otherwise, I guess I will see you probably in the GatherTown room if I can find it. Thank you all for coming. See you at my talk this time tomorrow, perhaps, on return value optimization and implicit move.